Everybody, this is me going over question 1 from the Rowan College of Burlington County Fall 2016 exam 1 for Mr. Walsh's class. This is question 1 of the open-ended questions. But this question here is all about kinetics and looking at the data without even asking what the question is. Or reading what the question is. My guess is this is going to be a method of initial rates. That's the way it always kind of works out whenever you see all this data going on here. Okay, so now the question is, write the rate law for this expression. So in order to do that, in order to write the rate law, we have to figure out what the values are for the order. And so when we do that, we're going to find two that are the same so that we can find this. So we're going to compare R1 to R2. Okay, and so this is going to be, okay, which is B over B naught. That little zero just means initial, and that's to some power n. Okay, so R2 over R1 is 8 over 2, and then that equals 0.48 over 0.12. So that's to some power n. So that's 4 equals 4 to the n, so n must equal 1. Okay, so now we have to do the same thing for A, and so we have to find two values where the concentration of B is held constant. So let's see, we're going to take experiment 2 and experiment 4. So that's going to be, and I'll come down here now because I'm running out of room. So R2 over R4 equals, let's see, make sure I get this correct, equals, the concentration, it's A naught over A naught, and all of that is to some power m. Rate 2 is 2 and rate 4 is 0.5, so this ends up going to 2 over 0.5 equals, and this is 0.24 over 0.12 to the n, or to the m, or whatever it is. Okay, so this is 4 equals 2 to the m, so m equals 2. So now we haven't finished, but we can write the rate law. R equals K A naught to the 2, and then B to the 1. And even though that's 1 and it's even though that's a 1 and you don't have to write it, I always like to write it. Okay, so now it says calculate the value of the specific specific rate constant, and you can use any one of these experiments 1 through 5 to do it, because you just plug it into this rate law. So for part B, let me get a little more room. For part B, you're going to use R equals K A naught squared B naught to the first. And now what's the rate for 1 is 8. And I'm just using experiment 1. K, that's what your K is what you're solving for. And then it's 0.24 and 0.48. So it's 0.24 squared times 0.48. Okay, and now we do K equals, we solve this, so we get 8 divided by 0.24 squared. Okay, remember, orders of operations is going to square the 0.24 before it does that, and then we're going to divide by 0.48. So your answer is 289. But now we want to make sure that we have the right units. So the units, in order to get the right units, we have to figure out what the units of this is. It's moles per liter, and then the unit of time is hour. Okay, so now we're going to do the same sort of thing. R equals K A squared B. Okay, and R is going to be in moles per liter times hour, and that equals, let's see, K, which we don't know, times moles per liter, and that's squared, moles per liter, because let's see, that's squared, this is just the one. So that then equals, let's see, moles to the third over liters to the third equals moles liter hour. So that means K, and I'll put it in a different color, that means that K has to be moles squared, liters squared, and then hours on the bottom. Okay, so your unit for part B of this problem is this. So your answer is going to be 289 liters squared mole squared hour. Okay, and now it says for part C to calculate the value of the initial rate for experiment 6. So here we're not given the rate, but we're given the initial concentrations. Well, guess what? We can still use the rate law, R equals K, concentration of A squared, concentration of B to the first. I guess we should put the knots in there to be good. Okay. And we know that this is 289. Okay, times A squared. A, I think, is 0.014. Okay, and 1.35, I'll remember that. So 0.0140 squared times 1.35. And so now you can, so this is me trying to keep everything straight here. Let's be awesome here. Woo! Okay. Okay, so you do 289 times 0.014 squared times 1.35. And so when you do that, you get a rate equal to 0.0765, and then the units of rate are moles per liter hour, just like it says right here, moles per liter hour. Okay, then part D. Okay, part D, I don't want to say it's a trick question. It's just a question that isn't a kinetics question. Part D is a question having to do with, let's see, stoichiometry. So we have A plus 2B reacts to form 3C plus D. That's the reaction. And it says that assume the reaction goes to completion. Assume the reaction goes to completion under, let me move this out from behind the kind specified, what would the, under experiment 2, what would the final molar concentration be? So for experiment 2, we have 0.24A and 0.12B. So let's go back here. So this is 0.24 here, and this is 0.12. Now when we solve this, we want to know how much of this we have. So the funny thing is when we do this, we just have to do a stoichiometry table or an ICE chart where we're going to go, well, which one's the limiting reactant? Well, this guy is the limiting reactant. So by definition, at the end of this reaction, that has to be 0. So this is minus 0.12. Okay, so that means this is minus 0.06, and this is plus 0.18. And so we get 0.18 molar here as our answer because we divide this by 2. For every 2 of these, we only need 1 of these. That's why that's half. And then for every 1 of these, we need 3 of those. That's why it's 3 times this much. And so that tells us what the final concentration is. Okay, so that's that's question number 1. So hopefully that clears any issues up. Have a great day.